Hello, everybody. Welcome to our session on autonomous operations for the Oceanology International Technical Conference. We've got three excellent speakers for you today. First up, we're going to have Mark Burnett, then we have James Cowles, and then Michael King. So I'll introduce my first speaker. This is Mark Burnett. He's the Chief Executive Officer of the SAISH Group, and he's going to be speaking on operating an unmanned surface vehicle, the wave-propelled Autonaut USV, around offshore infrastructure, including close pass maneuvers. So over to you, Mark.
Hello, as introduced, my name is Mark Burnett. I'm the CEO of SAISH Water Technology Group. I'll be presenting an update from SAISH regarding operating uncrewed surface vessels around offshore infrastructures, including close pass maneuvers. Before commencing, I'd just like to extend my thanks to the organising committee of Oceanology for the opportunity to present today and for the introduction from the session chair, Steve, for the introduction. So by way of an introduction and brief summary of the contents of the presentation today, I should be looking at three individual case studies which have each employed marine autonomous systems, MAS, for different applications and in differing operating environments. The first is a sound characterization study of a mobile offshore drilling unit, MODU, completed on behalf of BP, during which I will outline the study objectives, the project-specific challenges and safety considerations, the review and conclusion of which type of MAS was utilized for this project, and finally a review of the data acquisition phase, including the results. Case study 2 will highlight asset integrity monitoring for the ocean cleanup, illustrating use of uncrewed vessels to support the cleanup trials in the Pacific Ocean. And third, an expansive marine mammal baseline study located offshore West Africa, also completed on behalf of BP. So let's start with the first case study involving the sound characterization of a mobile offshore drilling unit, a MODU.
Yeah, Mark, can you share your screen, please? We can't actually see your screen at the moment.
My apologies. I thought that was sharing.
Great, that's great, thanks.
That should be online now. So first case study involves sound characterization of a mobile offshore drilling unit, a MODU, situated in deepwater environments in the Gulf of Mexico. An introduction to the MODU itself. This operation drilling unit utilizes thrusters for dynamic positioning to maintain position. And the objectives of the study were to acquire acoustic data within close proximity of the offshore facility. And secondly, to process and analyze the data set to update the historical limited measured acoustic data to determine both the sound footprint of the drilling unit and to use for future modeling capabilities. To perform this task, a combination of drift buoys and uncrewed surface technology was employed to acquire passive acoustic data to characterize the underwater sound field within close proximity of the offshore drilling unit to enable a comparison between measured and modeled data. There are a number of challenges and safety considerations associated with the project. First, associated with the data acquisition, spatial coverage, whereby there was a requirement to maximize spatial coverage whilst minimizing contamination from other sound sources so that we would only acquire sound at distance, so that we were able to acquire sound at distance as well as in close proximity to the drilling unit. In addition, the coordination of the deployment and recovery of multiple independent data acquisition platforms over an extensive area would be quite a challenge to manage in an active offshore oil field producing area. Secondly, SIMOPS, simultaneous operations, comprising both vessels associated with the oil field activity, namely standby and support vessels operating in and around the platform, complying with geophysical survey vessels operating adjacent to the study area, plus other maritime traffic operating in the area, cargo fishing vessels and the like. All of which would need to be considered and planned for with respect to vessel movements in relation to the autonomous data acquisition platforms and their respective sound emissions, which would potentially contaminate the acquired acoustic data of the drilling unit itself. And thirdly, the 500-meter exclusion zone with restricted and controlled access within close proximity of the drilling unit, which would require explicit permission from the client and the offshore installation manager, the OAM, to be able to acquire data within this zone, an explicit objective of the study. Taking operational and safety challenges into consideration, the planning stage was critical to accomplish the data acquisition requirements. To undertake the survey, we had intended to acquire data along transects on all 4 quadrants of the drilling unit to the north, south, east, and west. This included the need to acquire data in the far fields, out to 4 kilometers from the drilling unit, and the near fields, as close as practically possible within operational and safety constraints. The chart shows the proposed transects with a 1 kilometer space grid at the far field data acquisition and a narrow grid, nominally 500-meter separation, for the near fields in close proximity to the drilling unit. All transects would be subject to and dependent on SIMOPS and sea state weather conditions at the time, which would dictate the ability to deploy and recover equipment from the support vessel. To undertake this study, we evaluated a number of different platforms to determine which would be most suitable to acquire the passive acoustic dataset. Historically, as a company, we've used a variety of platforms to conduct studies around involving the acquisition of sound, including towed hydrophones from vessels, deployment of autonomous recorders, use of drift and moored buoys. For this project, we also considered the use of autonomous platforms that could acquire data autonomously, including uncrewed surface vessels, underwater gliders, autonomous underwater vehicles, and also potentially aerial vehicles, all of which have advantages and disadvantages when acquiring passive acoustic data. After the review, we determined that we would use a combination of both drift buoys and an uncrewed surface vessel to be able to provide the required data coverage at range and at depth from the drilling unit and take into consideration the SIMOPS activities. The safe drift buoys used are designed to record audio data and navigation data as they drift due to the effect of tide and currents. They consist of a mast housing strobe and radar reflector, metal top housing containing the battery and GPS tracking units, an E-tube which contains the data acquisition electronics, and a wet leg for additional ballast and stability, plus a hydrophone cable with hydrophones placed at 30 meters and 60 meters. The drift buoys are passive, non-intelligent data acquisition platforms. During the project, we did have a daily feed of information from the EddyWatch program available in the Gulf of Mexico, which provided intelligence to support the deployment and recovery plan to optimize the transect pattern and ensure avoidance of the 500-meter exclusion zone. Whilst the buoys would acquire data at depth, 30 meters and 60 meters, we'd not be able to use them within close proximity to the drilling unit. Hence the reason we also utilized an autonomous surface vehicle. The review process to determine why use a surface vehicle as opposed to alternative platforms was based on the following principles. Navigation, command and control of 2 different modes, able to set and monitor waypoints, track line to follow outside the exclusion zone and update on demand, and also navigation over Wi-Fi when operating within the exclusion zone itself. Cost, a significant cost saving in deploying a USV compared to a crewed survey vessel, typically 10% rougher order of magnitude difference in cost. And a well-known factor now of using marine autonomy, reduced HSE exposure by removing the requirement to have personnel at sea. So for this project, we chose to use the Autonaut, an autonomous uncrewed surface vessel. Specific specifications and prime specifications of the Autonaut being utilized being a 5-meter variant, which meant that we could air freight the vessel easily from the UK to the Gulf of Mexico with sufficient hull payload space. The ability to be remotely controlled over the horizon, and an autopilot system capable of autonomous waypoint navigation. Energy harvesting methods capable of both solar energy to recharge the battery bank and wave motion to create forward propulsion, allowing for long endurance mission. And equipped with a communication system and a hull-mounted passive acoustic monitoring system, including a 25-meter towed hydrophone array. With the Autonaut itself, specific advantages being a quiet platform, utilizing wave propulsion technology as opposed to an engine, which eliminates potential for contamination of sound of the data set by self noise. Zero fuel, therefore a cost saving and minimizing the carbon footprint of the platform. With demonstrated command and control capabilities, which provided the assurance of being able to maintain positional control with redundant and multiple communication systems, including satellite and Wi-Fi comms. Ease of integration of the SAISH micropam system, which was a case of just adding power and a GPS feed, with payload space suitable to accommodate the head electronic unit. Clean continuous power, and only consideration being the potential for contamination of the acoustic data should the auxiliary electric thruster be utilized at any point, and multiple attachment options for the hydrophone tow point. Plus relative ease of launch and recovery of the Autonaut itself. During operation, a standby vessel was utilized to deploy the equipment in the field. The vessel had significant side rails and freeboard. Thus a 2-point lift using the vessel's crane, plus quick release for deployment and quick launch for recovery. A key requirement for this project was to gain permission to operate within the 500-meter exclusion zone. This would be achieved once we had been able to demonstrate assurance of the remote control through waypoint navigation, whereby we could demonstrate heading maintained within 5 meters of track line. In addition to this, a detailed emergency response plan was developed and agreed with the client during the planning stage, including the requirement to have a standby vessel available at all times, so that in the event of a failure of Autonaut, whether as a result of communications, power, or mechanical failure, an emergency recovery could take place. The figure illustrates the data acquisition coverage that was achieved. The blue lines represent the Autonaut tracks, the yellow lines, the drift buoys. For the drift buoys, the prevailing currents were generally from the south or southeast, heading towards north or northwest. We took advantage of those currents to get a good spatial coverage of the far fields out to 5 kilometers from the drilling platform. Drift buoys were deployed outside the safety zone and during daylight hours only. The Autonaut completed transects to the east of the drilling unit to demonstrate full command and control, subsequent to which permission was granted by the client and OIM to enter the 500-meter exclusion zone. Conditions of operating within that zone included only operating during daylight hours, operating under local control, so Wi-Fi from the support vessel, having access to the DP2 capable vessel to be able to effect emergency recovery from the exclusion zone should the need arise. In terms of simultaneous operations management, this included interaction between the different data collection platforms, comprising both the buoys and the Autonaut, interaction of the data collection platform with the MODU safety zone, associated vessel traffic operating adjacent to and from the drilling platform, and the same for a second platform located to the northeast of the study drilling unit, plus the wider area vessel traffic, which included a geophysical survey being conducted to the north and to the west of the area of operations. Simultaneous operations planning and operation protocols enabled integration of our data acquisition efforts with daily activities of the drilling unit and attendant survey vessels. This involved reviewing the daily operational window of opportunity between other activities and daily area fleet calls coordinated by the client, including sharing a 24-hour look ahead for all vessels and planned activities. Key to the project was the ability to acquire acoustic data within close proximity to the drilling unit. The photo shows the Autonaut in the foreground with the drilling unit behind, showing a 140-meter close pass. Noting that the measurement is made from the navigation reference point on the rig, which is generally at the center, so actual closest point of approach was more likely sub 100 meters. Whilst it's recognized the impact of collision between an Autonaut constructed of carbon fiber against a steel structure of the drilling unit would be negligible, the requirement to provide assurance that the command and control will be maintained at all times whilst operating in very close proximity to the drilling unit remained paramount. The net result being the acquisition of a multi-azimuth rich dataset by Autonaut in close proximity to the drilling unit, combined with the drift buoy data at range and at depth. The results of the project were presented jointly by BP and SAISH at the 2019 Effects of Noise in Aquatic Life and subsequent technical paper published in the Journal of the Acoustic Society of America in November this year. Links to the papers are provided for further reading. A second case study involves the ocean cleanup project. whereby the team are aiming to remove plastic litter from the ocean, initially targeting the Great Pacific Garbage Patch using a surface barrier to accumulate plastic, which is subsequently removed, analysed, processed and recycled into high-value, non-single-use products. Autonauts completed a series of missions for the ocean cleanup, up to 50 days per mission, performing a number of functions to support the offshore operations. This included asset integrity monitoring. The picture illustrates a shot from the camera mounted on the Autonaut below the waterline, showing a close pass of the barrier system and its plastic retention curtain. In addition to the cameras, additional sensors included a hull-mounted ADCP, acoustic Doppler current profiler, to provide current information, plus meteocean sensors for wind, wave, and temperature measurement. A key functional requirement was the ability to operate within close proximity to the barrier system, normally at a range of 5 meters. To be able to conduct autonomous operations whilst the barrier was free floating in the Pacific Ocean, a navigation module was developed such that the Autonaut would follow the AIS transponders located on the barrier, with autonomous autopilot modes for fail-safe operations. In effect, the AIS position of the transponder, coupled with a defined standoff range, created a series of 3 waypoints for Autonaut to follow, which was updated at periodic intervals. Illustrated on the left-hand side, the diagram that the zigzag transit line completed by Autonaut maintains a position within close proximity to the barrier, but with built-in navigation logic to avoid collision. Third and final case study was a mission completed on behalf of BP between the islands of Sao Tome and Principe off the west coast of Africa. The project comprised a marine mammal baseline study utilizing passive acoustic data in a remote and extensive area between the islands of Sao Tome and Principe to understand the presence or absence, distribution and abundance of marine mammals over an extended period of time. To undertake this project, we operated an Autonaut from the island of Sao Tome, whereby the vessel was launched from a remote beach and sailed autonomously to the study area, whereupon the vessel conducted a series of multi-week missions in rather challenging conditions. During the project, we encountered strong and unpredictable surface currents, flat, calm seas, significant cloud cover, rapid bow fouling, and unintentional interaction with local maritime users. The strong and unpredictable surface currents would prevent Autonaut from maintaining transit line position under wave propulsion alone. And we had the occasional use to use the auxiliary electric thruster to offset the currents, which would in effect contaminate the acoustic data set. Further hampered by flat calm seas, resulting in reduced propulsion of the Autonaut, which relies on the pitch and roll movement of the Autonaut to induce forward propulsion. The significant amount of cloud cover impacted the amount of solar energy which would be harvested, which created a significant challenge to manage the basic power load required by the command and control, the autopilot, versus the sensor systems and the thruster, if so required. The rapid biofouling we encountered, despite the anti-fouling copper coat, still readily built up in unprotected areas, which impacted both propulsion and steerage efficacy. In addition, despite a significant local stakeholder engagement program, there was interaction with other marine users, which came across Autonaut, whilst deployed at sea, which proved a particular challenge. A further challenge and operation consideration was the value of the data set, which was being recorded on board, with the only information being transmitted via the Iridium SATCOMs, being a QC function to confirm data was being acquired and file size increasing. Consequently, intermission lengths were curtailed to effect a return to port of the Autonaut and recovery of data sets. In spite of the challenges that beset the project, with meticulous planning, we were able to acquire data over some 7,000 kilometers squared, which has also resulted in a very rich quality data set of the soundscape and characterization of the marine mammals encountered during the time period. Data has just finished being processed for this project, and data sets and outcomes will be published in due course. As a final slide on this project, the photo illustrates the conditions of the remote beach deployment for the project and a sample snapshot of the acoustic data acquired, which features extensive delphinid vocalizations, As with other autonomous operations, the use of uncrewed support vessel enabled data acquisition in a remote area with minimal infrastructure and local support. By way of a wrap up and summary, I've covered 3 different case studies which demonstrate the ability to acquire quality data sets using marine autonomous systems whilst achieving cost reductions in cost, in reductions in health and safety and security risk, and impacts on the environment's carbon footprint. In addition, we have demonstrated the ability to operate wave-propelled, uncrewed vessels in a number of different and challenging operation areas and scenarios, including close pass maneuvers with fixed structures, such as the drilling unit, and with dynamic structures, such as the ocean cleanup barrier. Further demonstrated the necessity to develop novel software to enable those applications, including the AIS track and follow navigation system, plus demonstrating over-the-horizon command and control capability and assurance by remote pilots located anywhere in the world. Quick set of thank yous. Thank you to client partners, both BP and Ocean Cleanup, for the kind permission to present the data in these 3 case studies. To colleagues within Station Autonaut for completing the projects with assistance in preparing the presentation. And also, last but certainly not least, for your time and for listening. And certainly happy to take any questions either during the panel session or via email, which is on screen now. Thank you very much.
Excellent. Thanks very much, Mark. Very, very interesting and always thrilling to see what the Autonaut vehicle has been able to, achieve in its use for our community. So thank you. We'll post some additional questions at the end of the session. So our second speaker is going to be James Cowles. He's the technical sales manager at L3 Harris, and he's going to be speaking on the autonomy toolbox for real-world field operations. So over to you, James, if you're ready to share your screen.
Yeah. Thanks, Steve. Hello, everybody, and thank you for taking the time today to listen to this presentation around the autonomy toolbox for real-world field operations. My name is James Cowles. I'm Business Development Manager at L3 Harris. So you might have heard of us before, but just under a slightly different name. So we've got a reasonably long history in autonomy, been doing it around 20 years now. Started off as ASV and around 10 years ago, had a bit of a rebranding, moved to a new location. And then just 2 years ago, were purchased by L3, who subsequently merged with Harris to bring us to our identity today of L3 Harris, which is really great for us as a business and really strengthened our capabilities, bringing in unmanned underwater vehicles and unmanned aerial vehicles and a range of other technologies that we're able to access from across the group. We've, as I say, been doing it for a while. We've now delivered over 100 systems, and that's ranging from 3 meters to 13 meters, which is the vessel you see on the screen here. And what we're doing is redefining the way the world works at sea. And what we mean by that is that the world is changing dramatically at the moment. And as Mark highlighted in his presentation, the need to keep all of our mariners safe is ever increasing. And the ability, therefore, to increase jobs ashore for those personnel is a significant benefit of unmanned technology. And then also, in some scenarios, what you want to do is, rather than having a single large vessel, you want to have multiple small vessels to increase your coverage. And that's where we're trying to bring the unmanned technology to bear and enable our customers to go and deploy that in a wide range of environments, from commercial survey to military for force protection and mine hunting. So more on to autonomy. I think what I like to do first is just kind of outline what, when we say autonomy, what do we mean? It's a bit of a continuum. People will say, oh, autonomy, and what they'll be thinking is just you press the button and off it goes. But in the marine world, life is never quite so simple. We've got to ensure that the vessel is operating safely, ensure it's operating in line with regulations. And a large portion of that has to be attributable to people. And you do need to have somebody on the end of it who is there to support it in the harsh marine environment. And whether that be through remote control or through just allowing the autonomy to take its course, but ensuring it's safe, there's a wide range of support options there. So autonomy is often broken down into 5 different levels. So remote piloting and basic autonomy is something that we as L3 Harris and ASV before that have been delivering for nearly a decade now. And that is the broad amount of what we're delivering today and will be delivering in the future. But what we have started to deliver to customers is advanced autonomy, which is level 4. And what that means is not only is the vessel going to do what it's told, and not only is it going to look at what's going on around it before it starts, it's going to be maintaining continuous watch, so that it's not just avoiding land or vessels that it knew where it was when it started. It's constantly looking around it, assessing its environment and ensuring that it is operating safely. Ultimately, we do want to get to level 5, and that's something I'll talk about towards the end of my presentation. But it's a way off, and I think we're always going to be wanting to enable these vessels to be monitored and supported by the human, because ultimately computers are good at very logical based decisions, but every now and again you get a complex scenario which needs the human intuition to enable a correct decision to be made and ensure safety. So what does this autonomy look like from a point of view of control of these vessels? So you start off with data. Now, it's not on the sea, data is not a static thing. You do have some static things such as charts, waypoint plans, geofences, and that's all fed into the system in the back end. But actually the dynamic nature of the sea means that data is always changing. So you've got radar coming in, camera data, AIS, which is all filling into this world model. And then what's important part of the way we deal with this world model is we're also looking at future world models. So we take that radar data and that AIS data and we project it into the future. And I'll talk a bit more about how we're developing that functionality later on. And what this means is that we can give the vessel in its autonomy some of the sort of attributes that people put on data when they're at sea. When you're a skipper and you're helming a vessel and you look out to sea and you can see a container ship coming across your path, you don't just look at it in the position that it's in. You use your intuition to project that forwards in time. And what we're trying to do is imbue that onto some of the vessels that we're designing and building at the moment. So then on top of this data, what you get is a risk map. So you know that the sea, for example, the land, for example, is very high risk. A vessel coming across your path is also going to be high risk as well. And we plot that in a 3D space so that you can see area as well as risk. And then on top of that, we put the other behaviors that we want the vessel to perform, such as the collision regulations avoidance. And what that means is we force the vessel to do what people would do. So if a vessel is coming up across from the starboard side, you will extend that risk bubble further in front of that vessel so that the autonomous vessel would automatically look at that and go, well, actually, the safe low risk path is to go astern of that platform. And that means that we can force the vessel down the route of following collision regulations. Now, our system at the moment is what we call collision regulation aware. It's not got the same level of knowledge as someone who's been doing it for 20 years, but it has got an understanding of all the basic collision regulations and is able to avoid other vessels in its path and in the surrounding areas in a way that a normal mariner would consider appropriate. So by that, what I mean is it does take action early. And once it's taken action, it sort of sticks with that. It doesn't flip-flop between 2 different options. So that gives other people on the sea the certainty to operate as they would normally. And that's what we're trying to achieve with this. And the way it does this is in 3 different layers. Number 1 is the route planner. So as you would do, if you were leaving Portsmouth Harbour and you wanted to go around to the back of the Isle of Wight, you would think in your head, right, I've got to go out through the entrance to Portsmouth Harbour, turn to port a little bit at the forts, go round Bembridge Ledge, and then round to the back of the Isle of Wight. And the vessel does much the same thing. It will plot that route. But then what it'll do is, as it starts executing that route, look a mile or a few minutes into the future and go, is there anything that's going to impact on my route? And then that'll enable it to make a course correction on those waypoints to ensure that it maintains safety. And normally that is all that's required. Those two levels of planning will enable a vessel to operate safely. However, as I imagine we've all experienced, not everybody at sea understands the rules or follows them. Some people do make erratic changes. Some people don't maintain a good lookout. So that's why we've built in this last line of defense of the last response engine. And what this is that takes into account not only where the vessel's going, but importantly, what trajectory it can achieve. So is it a small, nimble vessel, or is it actually a big, slow vessel? And what that'll do is then when something comes into its last response zone, it will make a decision on what it'll do. And we very purposefully kept these decisions very, very simple. So that this can be the safest, most assured code that we use on our platforms. So the vessel will either turn to starboard, as per the collision regulations, slow down, or stop. And it's important to note this is, as we say, a last response. This shouldn't be happening unless there's somebody else at sea who is not obeying the collision regulations, or, as can happen in a degraded environment, the sensors have not managed to pick something up. So what this does is gives the system a really clear way to operate and plan its missions. And then on top of this, we can also layer other behaviors, such as maybe protect and patrol around another vessel. Maybe it's always maintain position. Maybe it's follow, something like an underwater vehicle. We can layer these behaviors up in a way that I'm going to talk about a bit later on. So some other areas of development for us is kind of split across three core areas. Vessel control. So how do we guide these vessels once we've got the data? Following paths, so other platforms, things like that. And how do we control our actuators in the best way? Intelligence is the core of what we're developing at the moment, which is really around how we take data in and how we make decisions on that data. So some of the things I've talked about already, such as bringing in data from AIS and radar, and how we do collision avoidance. But this has got to be built on good data, which is all about perception. So what cameras are we using and how are we using them? What chart data are we using? And can we get data from external sources, either that be that tracks from another radar system, AIS from satellite systems? How do we get that data back? And then how do we present all of this data to the human? So this is all areas that we're developing, and we've got working prototypes in every area here that's showing an increased ability for the operator to have situational awareness and execute a mission in an efficient way. One of the things we've been working on recently has been target following using cameras only. So this is going to come into its own when we're starting to talk about autonomous docking and things like that. You can see the vessel here is following a icon on the back of a vessel. Now we've used the icon specifically because that allows the camera to track that vessel and also to enable it to know how far away it is. Whereas if you didn't have that icon, you wouldn't be able to know how far away it is, just the angle. And we've been developing the precision of this to enable us to dock a vessel of that type into a cradle. And then talking about how we move forward in a confident way and understanding further and further ahead what other vessels are doing, we've been working on channel classifiers. And looking specifically at places like the Solent, what we can do is say, well, this vessel is a large container ship. Therefore, we can predict where that vessel is going to go. So, for example, if it was coming in through the forts near Portsmouth and it was a large container ship, we can predict with very high accuracy where that vessel is going to go. We know it's going to follow the channel to Bramblebank, and we know it's going to turn to starboard and go up Southampton Water. And what that does is it enables the autonomy to make decisions earlier and earlier. So this is what it looks like under the hood. You can see that there's a number of vessels and there's a number of different courses. The vessel in the middle here, you can see it has a number of different routes. Because it's a small vessel, it's harder to predict. But whereas the bigger vessels, we can predict very confidently where they're going to go. So those are some of the things we're working on. And you can see now in the video coming up some of the trials that we've been doing. This is the MAST 9 platform we work on with DSTL. And what we've done here is turned off of the advanced autonomy, and we're solely using a small radar to do collision avoidance on structures in front of us. And as you can see, the buoy in front of us was detected very early, and we can make a really clear, safe turn to starboard. And some further views of the follow behavior, what we're looking at with regards to some of our camera vision, which if you're interested more in our vision systems, I really encourage you to listen to a talk from one of our data scientists, Hannah Thomas. It always impresses me when I hear a talk, even if it does blow my mind a little bit. Here we can see what the result of some of our autonomy is. So this is the MAST 13 platform owned by DSTL and operated by L3 Harris. And we performed an operation where we approached within 12 miles of the coastline of France using our advanced autonomy systems completely unmanned. So the vessel was operating at 40 knots for over 3 hours, using the WESCAM system on board to ensure situational awareness and also detect other hazards in the area. What this enabled us to do is just really demonstrate how the robustness of the collision avoidance autonomy that we've developed, and was a really great showcase. But all of these different bits of functionality are lovely in themselves, but actually what we need to do going forward is enable the autonomy system as it's so developed now to make some of these decisions itself, take some of these individual behaviors, or what we call them primitives, and build a set of behaviors out of that. And then actually link a number of sets of behaviors together to create a plan and enable the vessel, based on its sensor input, to choose which of these plans it's going to execute. So what we're looking at is taking primitives. So things like follow this from this distance, do an orbit here, follow this line, but then add a level of conditions to those. So the different conditions might be weather-based. They could be distance-based. So in a military example, it could be something along the lines of, I want you to protect this frigate. However, if another threat or something comes within 500 meters, we want you to go and investigate it. So what we're doing is enhancing the level of autonomy that the platform will bring, and therefore reducing the load on the operators. So the operators can then maybe concentrate more on, say, the camera data that's coming in and analyzing what that's saying. Or in a survey example, if the line plan is planned in such a way that actually the data is not coming in good, we can alter the line plan in real time to enhance the data quality. There's a whole range of possibilities. And the other side of this is we develop this in a way that we can work with people like scientists and customers to develop different behaviors based on the primitives we have available. And that gives a great amount of flexibility to the system. So now we've got this, that's great. But actually what we want to be able to do is take this another step further. We want to take these groups of behaviors and develop strategies so that we can give the vessel more possibilities for how it can decide what task to do. And ultimately what we want to be doing is letting the vessel choose which either strategy it's going to take forward. And that's going to take the view of goal decomposition. So rather than having to define the strategy for the platform, what an operator will be able to do is say, I want you to go and do X. And other things we're working on in the background to support this are things like a heterogeneous comms network. So when you've got multiple platforms, maybe multiple platforms with different capabilities, the system will be able to detect those capabilities and then assign a strategy based on either vessel capabilities or the goal that's been trying to be achieved. So that ultimately we can have the greatest level of flexibility and really enhance the value that an operator brings to this scenario. If it's a simple mission where the vessel can control itself through parameters it knows on board, let it do that. And then let it flag to the operator when either it can't complete the mission or there's an issue on board. And if there is an issue on board, you don't want to have 500 different notifications of different things. What you want to have is one notification of what the core problem is. So how do we respect that operator's attention? So thank you very much for listening to me. I hope that was interesting and can demonstrate where we're going with autonomy and some of the missions that we've been achieving recently. Thank you.
Excellent. Thanks very much. Another really, really interesting talk, and I'm sure that will generate some good questions from the panel very shortly. So our third speaker is Michael King. He's the Senior Business Manager at Senior Business Development Manager, at Ocean Infinity, and he's going to be speaking on the multi-AUV operational model. So over to you, Michael.
Yeah, thanks, Steve, and hi everyone. Thanks for tuning into this session. Yeah, I'll launch straight into it. So you probably know a little bit about Ocean Infinity already, but to give you an update for those of you who aren't too familiar with us, we were founded in 2016, and since then we've been working on global projects utilizing multiple autonomous and uncrewed robotic systems. And we really try and focus on what can be achieved with the innovative and collaborative use of the most modern technology available. You know, from large-scale hydrographic mapping to search and salvage projects in thousands of meters of water depth. As you know, some of our projects have made international news, but we've also conducted countless smaller and commercial projects across the world. And as I mentioned, our ethos is the use of multiple systems, primarily for force multiplication, vastly increasing efficiency and project delivery, although we have a real focus on minimizing our carbon footprint and providing some of the most sustainable offshore survey capability on the planet. Now, the future focus of the Ocean Infinity Group is certainly on our new Armada fleet, which is currently under construction. And this will see a fleet of 21 meter to 78 meter uncrewed robotic ships operating globally, providing remote and efficient data acquisition and logistics services to a wide range of maritime industries. I encourage you to check out my presentation on our Armada fleet in the other autonomous operations conference sessions to learn a little bit more. But today, I really wanted to talk about our multi-AUV operational model and share some of the details and share some of the case studies from this capability that we've been operating for the last few years. So as I said, since 2016, we've invested very heavily in the world's largest fleet of commercial deep water AUVs, and we currently own 14 Hugin 6,000 meter rated vehicles. Now we currently operate them from conventional ships, each with the capability to deploy multiple vehicles simultaneously. And we can deploy multiple AUVs simultaneously, but our vessels also have work-class ROVs rated down to 6,000 or 7,000 meters water depth. We have multiple USVs on board to provide positioning and shallow water survey services. And our larger vessels are really very much a toolkit for offshore uncrewed and autonomous survey. Regarding our vehicles themselves, the AUVs are equipped with the world's most advanced hydrographic and geophysical sensors. And through partnerships with various key battery and operations technology providers, all of our vehicles have single dive mission lengths far in excess of industry standards, allowing us to push that operational envelope even further. Now, since 2016, we've logged even more commercial AUV hours than anyone else, allowing us to really know even more about our equipment than most, and it allows us to get even more out of our technology, which really adds to our model itself. But why approach the use of AUVs differently, as opposed to following a fairly standard single vehicle model that has served a range of industries very well over the years? Now, Ocean Infinity believe that leveraging technology and pushing the boundaries of what is capable has direct benefits, and we believe we've proven this over the last few years. Some of the advantages of a multi-AUV model. Now, depending on the resolution of data sets required, of course, but our multi-AUV model with 8 vehicles in the water simultaneously can generate up to 1,100 kilometers squared of seabed survey data in a 24-hour period. Anybody who knows their AUV survey knows that that's a vast quantity of data, which really allows the rapid completion of offshore projects. It also allows the optimization of offshore personnel levels. The staggered launch and recovery of the vehicles means that we don't need 8 individual AUV crews on board. We need fewer technicians, we need fewer operators, we need fewer mechanics and engineers. And this really allows us to reduce offshore headcount as much as possible. That reduces offshore exposure hours, but it also reduces the need for multiple vessels. So we can do all this off a single ship. It also gives us a bit of natural redundancy. We can carry more than the number of AUVs required on a project. Therefore, we get natural redundancy of a whole vehicle and sensor package in itself. But it also means that there are more capabilities to install additional vehicles onto a project. We have advantages in remote locations, far from ports, in parts of the world that are difficult to ship equipment and replacement vehicles to. So the risk to clients using a multi-AUV model is far reduced by the ability to have that redundant system on board. And above all, this leads to a quite staggering reduction in emissions. You only have a single vessel, which is only slightly larger than a traditional single AUV ship, yet it provides survey capability far in excess of that. And this really allows us to minimize not only the exposure hours that I touched on earlier, but the overall emissions on a project. So I wanted to spend some time running through a couple of case studies just to kind of showcase the different elements of the operational model that we've adopted. As you probably know, Ocean Infinity ran a 2018 campaign to apply this multi-AUV technology to the search for the missing aircraft MH370. No one knows quite where it is, of course, but it is believed to lie in between 4,000 and 6,000 meters water depth along the so-called 7th arc in the southern Indian Ocean. The seabed conditions in this part of the world are incredibly varied. It's a huge amount of seabed to be looking within, which means that you get a huge amount of variation in that topography. So it varies from relatively simple flat abyssal plains right through to the complex bathymetric environment of the Broken Ridge seamount. And this really requires the fact that you need AUVs to do this work. There are incredibly complex seamounts, incredibly complex canyons and ridges, and even deep tow systems just cannot achieve the resolutions required to search for something so small in somewhere so large. However, sadly, after 138 days and over 125,000 kilometers of seabed search, the aircraft remains missing. And there are constant discussions about re-enlisting that search to carry on. To give you a bit of comparison between the multi-AUV model and a single AUV model, what I've done is I've looked at two different search campaigns. So initially, after the vessel went missing, the Australian Transport Safety Bureau commissioned a search area to be undertaken, which is that red area, as you can see. And this was conducted using 4 vessels, totaling 837 vessel days. The total seabed covered was 121,500 square kilometers, which is a huge volume. But the difficulty there is that actually there was some lower probability of detection areas. So just over 2% of the information, once processed and once the data had been reviewed, was actually viewed as a lower probability of detection. And one of the problems there is that, until you can have some confidence in your data and some confidence in all of your data, there's every chance that the vessel went over the airliner, but it was unfortunately unable to locate it. The other thing to bear in mind is because 837 vessel days is a large number, and they're large vessels operating this part of the world. The vessels themselves burnt just over 12,000 tons of fuel and subsequently emitted just shy of 40,000 tons of CO2 over that 837 vessel days. Now, to compare that to the multi-AUV model that Ocean Infinity employed, as opposed to the single AUV model that was used on those other ships, you can see that variation there. So Ocean Infinity were able to provide a much more efficient and rapid data acquisition capability, with far fewer areas being in those lower probability of detection criteria. And there's actually a greater area of seabed searched in just over 15% of the vessel time. So that really shows you the advantages of the multi-AUV model. Now, another aspect that can't be ignored in this is the subsequent reduction of emissions, like I touched on a couple of slides back. The use of only one vessel with a multi-AUV approach yielded a 75% reduction in emissions of CO2 for the search campaign, not to mention the significant reduction in exposure hours as well by only having one vessel offshore. The second case study I wanted to talk about was a little bit more of a commercial case study. I wanted to share some details of a route survey completed using the same operational model. Now, this was a pretty complex site. It required high resolution bathymetric data sets down to over 1,500 meters water depth, as well as multiple other sensors acquiring simultaneous data. The other thing to note is this project took place in the winter. Therefore, the need to take advantage of operational weather windows was key. So a multi-AUV rapid acquisition solution was proposed by Ocean Infinity to our client. in order to showcase the capabilities of the system, we proposed a multi-AUV solution, as I said. And to give you an idea of the size of the project, we collected approximately 7,000 line kilometers of AUV data. We actually achieved this using the multi-AUV model with 0 weather downtime, because we were able to limit our offshore exposure to about 20 days. And the other key point is that because of the way that Ocean Infinity acquire and represent their data back when the vehicles return back to the vessel, that high resolution bathymetry data particularly was available immediately after vehicle recovery. And this allows development decisions to be made in real time. And actually, you can see there on the bottom right that we were able to recommend and therefore go ahead and survey a slightly different pipeline route for the client. And all of this leads to, again, a 75% reduction in operational time, as I've already touched on, compared to a single AUV vessel, but also quite a significant reduction in the cost as well. A single AUV vessel costs a certain amount, and whereas the Ocean Infinity model does cost more on a daily basis, the huge increase in the amount of data acquired in those 24-hour periods really does make a big difference. So just to summarize some of the case studies I've talked about, the multi-AUV operational model allows a step change in the scale, the precision, and the speed of offshore data acquisition. We enjoy far greater levels of sustainability, and we can achieve this, as I said, through force multiplication using those robotic and uncrewed systems. But the truth is that none of this model would be possible without the world-leading team of experts that we rely on for these complex operations to be planned, executed, and reported. And the team at Ocean Infinity are well versed in this model. They're well versed in the use of incredibly complex technology to really leverage those advantages that I talked about. And we're pleased to be able to continue to offer this to our clients around the world. So thank you for tuning in. As I said, I encourage you to check out the other session that I recorded to learn more about the Armada fleet itself. But as I said, by all means, reach out by email or on LinkedIn on the details on screen with any questions that you might have. So yeah, thanks very much. And that's back to you, Steve.
Excellent. That was really, really interesting. And I think all of us would agree that we're entering a really exciting new era in offshore survey, and how marine autonomous systems have certainly transitioned from being lab rats, things that are just used on an experimental basis, into being real hardworking technology that's bringing multiple benefits to both civilian users, industry users, and defense sector users as well. So a fast changing world. Certainly there are aspects where perhaps the legal and policy side is sliding a long way behind where the technology has moved on as well. And I think we're certainly seeing that in the defense sector and in applications such as what happens when you arm robots. You're into some very tricky legal spaces there. But we've got a little bit of time for some questions. Because of the way this has been filmed, viewers, unfortunately, we're not able to open the Q&A session to the general public. But what we are able to do is ask some questions within the panel. So I've got a few up here on my chat box to kick things off with. And the first one is a question from Michael to Mark. And he's asking about what operational and deployment changes would have to be made to allow marine mammal observations live on a project to fulfill the requirements set out by the various regulators and governments. And he's meaning this in the survey sense. Do you want to expand on that, Michael?
Yeah, I can do. I mean, as you're no doubt aware, Mark, there are some quite stringent kind of marine mammal observation requirements, particularly in the US, but also in other parts of the world, requiring live observations both before and during survey operations, not only for seismic gear, where obviously you're putting a lot of power and noise into the water, but also some of the more hydrographic equipment as well, requiring a window of no marine mammal observations before even starting those kind of operations. So I guess I just wondered, you talked a little bit about a marine mammal baseline survey that you guys conducted. I just wondered whether you'd need to change that in order to provide a live marine mammal observation alongside a survey project, I guess.
Yeah, it's a fundamental question, and it's a very key one that is being addressed at the moment. So yes, the case studies that I presented there were all about recording data on board and then subsequent processing of that data. key to any mitigation is having that live data field, the live data stream, to be able to make instantaneous decisions on the data or the information. Key to that, two elements really. One is either increased capability of sending data from your remote vessel to a person in the loop. That it both has an impact on cost. You know that satellite time is not cheap, so increasing bandwidth, unless your remote platform is within a radio or wireless Wi-Fi range of the platform itself. The second alternative is the actual onboard processing of data, and so just receiving the information and then transmittal of that information back to a central station to make decisions. Part of that is therefore the increased onboard processing capability of being able to, in the remote mitigation sense, be able to form onboard processing, detection, and classification and localization of the particular target that's been identified, and transmitting that information back to a central point.
Yeah, that's certainly the way we at Ocean Infinity see it with some of our Armada operations. Is if you can do a certain amount of automated processing offshore, you know, without a human in the loop, you can almost send back a green light or a red light saying, you know, I mean, in this case, yes, you're good to survey, or no, you're not good to survey because of whatever it might be. So yeah, if we can automate processing, I guess that becomes a much easier data transfer option.
Yeah, and as part of that, the platform itself potentially lends itself to be able to make that processing more of a quality processing routine, where the data is not masked. So particularly, I guess, the low frequency animals, which potentially masked by vessel noise, with having a quiet platform, the signal to noise ratio at least gives you a fighting chance to be able to process the data, as opposed to narrow band, high frequency clicks, which are much more readily able to be detected and discerned, and therefore provide information on a target identification.
Great.
Okay. Excellent. Thanks very much for that. Next question's from Mark to James, and he's talking about the sensor inputs, you know, the radar, the cameras, the AIS systems. Are these weighted in the track fusion model? For example, in a degraded environment such as fog or heavy rain, are they more reliant on sensors that are not so susceptible? And this is quite similar to the separate question I'd also posed to James, which is how well do these kind of systems work in a GPS denied environment?
Yeah, so I think on the sensor input side, it's really quite a challenge to do. And actually, one of the things we're developing at the moment is how to actively look at the operational picture we've got, and then change how the settings in, say, the radar. AIS is kind of pretty simple. If it's bad, it's just going to be a shorter range. But the radar is a challenge, because what you need to do is to optimize that picture through changing the settings. And that's something we're looking at how we can do actively at the moment. To sort of move on to the GPS denied environment, this is a bit of an interesting one. The system is somewhat reliant on position, but not therefore necessarily GPS. So there's a number of methodologies that we're employing to mitigate challenges around the GPS, and also to in part identify if we are having problems with GPS. Yeah. So the simple ones are we can use INS systems and things like that to cover short outages in GPS. Same with, as you would with a DP ship, use acoustic subsea positioning to do the same thing. We've run demonstrations of small vehicles just running solely off underwater positioning. But one of the more advanced things we're looking at is how we can take things like chart data and the radar data that we're getting from the vessel to cross-check our GPS position. So does the coastline that we're seeing it around us, does that match the chart? And if it matches the chart, great. But does then our position relative to that coast also match? So it's a sort of a multi-level thing to how we can operate. But yeah, GNSS denied environments are a big next step for us as well.
Yeah. Okay. No, thanks for that. And then our next question, we have one from It's from James back to Mark, asking, do you see larger autonauts being produced, and what benefits do you think this would have?
Thank you for that question, James. Two-part answer, I think, on this one. I guess the first part is, do I see use of wavefold technology on larger vessels? Yes, absolutely. It's a function of capability of engineering to use pitch and roll to induce forward motion through foils. It is an engineering challenge being able to engineer up a system moving away from a fairly lightweight carbon fiber vehicle platform up to a significant structure. But it's not beyond the bounds of possibility where we're looking to reduce the amount of carbon used for shipping in general. In terms of the actual Autonaut platform as it exists today, likewise, there are plans to increase the size of the Autonauts to be able to have both increased payload space, sensor space, and increased battery space, either through the use of fuel cells or increased batteries, to be able to increase both endurance at sea. So in an example, in a low solar power environment, whether it's high latitudes or during hours of darkness or in the winter months, being able to have an increased battery payload or fuel cell, and then combined with the actual sensor package itself. It'd be great to have a winch capability, for example, to be able to deploy a sensor closer to the seabed or in the water column. Things that are on the shopping list, really, of dreams of where Autonaut platform technology could go.
Okay, thanks. Right, and Mark's got a question here for Michael. Is there an optimum model for the number of AUVs that are utilized?
Excellent question, and it's one that we spend a lot of time asking ourselves when we're project planning. The honest answer is yes, there is for every application, but it's almost never the same answer, because you're right, it's incredibly application dependent, not only in terms of the data sets you're acquiring themselves, but also the survey area itself, the kind of the dimensions of it, the size of it, how far apart you're expecting the AUVs to be operating. You know, if you operate them quite close together, then some of the sensors interfere. So if you're on a really small area, then you kind of think, well, you know, let's get it done in a few hours by chucking loads of AUVs at it, but that doesn't actually work very well. Likewise, if you've got a huge area, then to be able to track them all simultaneously, you need to be able to either position them in the same area using the vessel, which in deep water is quite easy because the high power system we use on board for subsea positioning has kind of a cone of influence that in deep water is obviously very large by the time you get to depth, but in shallower water you need to use additional uncrewed surface vessels to provide positioning downwards to AUVs. So there is no optimum model off the bat, but certainly for different jobs we use different numbers of AUVs, anywhere from 2 up to, as I said, 7 or 8 in the case of some really deep water large area surveys. But it's very much a conversation that needs to be had with our clients to establish what their buying motivations are. You know, is it speed? Is it accuracy? Is it both? Is it, you know, there isn't a simple answer, unfortunately. But I also noticed another question there that I'll cover off at the same time about the battery technology that I talked about. In that their, you know, increased endurance of AUVs is obviously really important. So those Hugin 6000s kind of off the shelf from Kongsberg at 4 knots survey speed will do about 60 hours in terms of mission length before they need to be recovered and recharged. And of course that includes dive time and recovery time. So if you're in 3,000, 4,000, even 6,000 meters of water, it can take a couple of hours, you know, even up to 4 or 5 hours to get to depth and then to come back up to the surface again. So that's something that really has to be factored in. We have a partnership with a company called Kraken Robotics, who I'm sure you'll have heard of, who amongst other things, you know, engineer and build battery technology. So we have Kraken batteries in our AUVs, which gives us mission lengths in excess of 80 hours per AUV. So by increasing it by, what's that, kind of 15, 20% maybe, you're actually enabling a lot more what we term bottom time for the AUVs, because not only are you increasing the length of time it can be in the water, but you're also increasing the length of time you can actually be acquiring that data. And of course, if you're running a vehicle with lots of sensors simultaneously, those batteries drain even faster. You know, if you're running sub-bottom profilers and kind of power hungry equipment, then those batteries are really, really critical. So yes, it's better to have increased endurance, but of course it's better to have more AUVs on certain projects as well. The less time you spend recycling those AUVs, the better, and the more efficient you're able to be.
Okay, thanks. And Michael, we're recording this on the 23rd of November, and I saw a press release this morning talking about the 78-meter autonomous vessels for the Armada project. Are you able to tell us anything more about those?
Yeah, certainly. So unfortunately, when I recorded the Armada presentation for Oceanology last week, the press release hadn't been made yet, so I wasn't able to talk about them. So yeah, some fortuitous timing. But yeah, as you said, there was a press release this morning from Ocean Infinity, just claiming that we're building our first fleet of even larger vessels. So we've committed to building 8 78-meter ships, and they'll be built by the Vard Shipbuilding Group, with the first one due for delivery in mid-2022. And these are just the next step in our ambitions to change the way that kind of offshore operations are conducted. These vessels are being built to be crewed initially. They've got berth space on board for 14 or 16. So that the idea is that all the back deck operations will be automated and uncrewed, but we're not naive enough to think that we'll be able to sail a 78-meter vessel around the world without anybody on board by 2022. So they're certainly being built to be able to be operated uncrewed, but we're certainly of the opinion that we will need to put crew on them for a few years. So they're being built to be able to work straight away, but certainly with half an hour in the future, in order to kind of take those people off the vessel themselves and move towards an even more robotic and automated way of operating. The other thing to note that's really interesting is we're building them to be able to be retrofitted with ammonia fuel tanks.
Right.
Enable ammonia fuel cell technology when that becomes, omnipresent enough to be a viable option around the world. Because, as I said, we've got a real focus on sustainability, and it's our desire to kind of move towards a truly net zero operating model for large boats as well as small vessels. Of course, we need our suppliers to kind of come on this journey with us. And one question I had for James, actually, if I may, just
please do, yes.
Ruin your flow, Steve, from the questions you've already got. But obviously, L3Harris are providing the control systems for our smaller Armada vessels, and we'll continue to discuss things, along those as well. But in terms of taking the existing tech that you guys are building for the vessels you provide, and also providing it as a third-party service, and moving that into a much larger vessel kind of environment, is that something that L3Harris have got ambitions for in terms of moving their autonomous control system into much larger areas, or is that kind of a step that's probably a bit challenging at the moment, as I said, with all of the regulations?
I think, yeah, there's a level of challenge to everything, but that's what we've been delivering for the last few years anyway. So yeah, definitely keen to look at the larger vessels. And I think one of the things we're really seeing as we move into that area is that on smaller vessels, the engineering systems aren't really that big. You've kind of got a pretty simple engine, you've got a pretty simple build system. But then ultimately what we're looking at as we move larger and larger is that sticking more to L3Harris's core technology, the stuff I was talking about in the presentation. So collision avoidance, mission planning, situational awareness. So more the navigation side of the operations. And there might be businesses better placed to deliver the engineering side. We've got businesses within L3Harris called MAPS that do integrated platform management systems for things such as the Queen Elizabeth carrier. So they're an option, but also businesses like Vard and like other shipyards do platform management systems themselves. So there is a discussion there about bolting onto that system, or that system bolting onto ours, so that we can create a relatively seamless thing and treat it a bit like you would a large ship, where you have an engineer who's controlling all of the engineering side of the vessel, and then you have a navigation officer who's doing the navigation through something like ASU.
Yeah. Okay. Thanks.
Okay, thanks. So we've just got a couple of minutes left. Can I open the floor up to any of you who'd like to ask anybody else a question? Otherwise, I'll throw one in from me to any of you who feel free to answer it. The legal and policy space that we're operating in at the moment, it's reasonably well defined, within the territorial waters or the exclusive economic zones of member states. But there's still quite a few gaps in the legislation, particularly when you move out into the high seas. So are there any priority areas that as a community we need to be working on to make sure that the legal and policy space is ready for this revolution in autonomous systems as well?
Well, I'll have a crack first, shall I? I'm sure everyone's got a word for this one. I think actually this is where the challenge of larger vessels comes in. Below about 24 meters in general, a lot of the regulations you can kind of box off relatively well, with good supervision. Good communications is a major challenge when you're going up that far offshore, to certainly do the regulations. But once you're over 24 meters, and there's a lot of stuff around SOLAS, STCW, a whole bunch of regulations that there's no current way for either a nation state or an operator or manufacturer to say, oh yeah, we comply with these, because they do some really broad brush things around, you will have X and you will have this many people and these people will do these jobs and they'll be on the boat. That creates a bit of a challenge. Hence why a lot of the platforms we built today are below that 24 meter and size and weight bracket.
Sure. Yeah. So there's still a challenge there. So the technology moving faster than the lawyers can keep up, I suspect. Yeah.
I think just to add in there as well, Steve, it's as James presented on levels of autonomy as well. And at what point you move away from having a remote pilot in the loop providing remote control or remote oversight through to full autonomy. And there's certainly the way that the industry is moving is towards that full autonomy capability, which will take some time. Hopefully by then that the marine regs will have at least had some catch up, but it certainly is an absolute necessity to get there as a parallel journey.
Yeah, I mean, we're working with a number of regulators, as you might imagine, bearing in mind the vessels we're currently building. And yeah, both Mark and James are spot on with regard to the kind of the 24 meter cutoff. The sub-SOLAS category and levels of autonomy, and a kind of a stepped approach in this. As I said, we're certainly not planning on launching a 78 meter boat uncrewed from day one. It's just not practical. But I think the important thing is that new vessels and new projects and new programs are designed with an eye on the future, because we're certainly going in the right direction, and we will certainly get there within not too many years. So I think it's important that current projects and current builds and current kind of concepts of vessels and equipment and things like that are very much, you keep an uncrewed and an autonomous view over the whole thing, because if you build a ship now, for example, that's completely conventional, that's fine, but then autonomizing it later is probably quite difficult. Whereas if you build something at the moment that at least has the capacity to be operated uncrewed, be that a ship or a drone or an underwater vehicle or whatever it might be, then at least it gives you that chance to do that in a few years when the regulations do catch up with the technology.
Excellent, thank you. Well, it's an honor to speak to all of you, to be honest, because we're at a point where, as we mentioned earlier, this technology is moving away from science fiction and experiment into day-to-day reality. And when the history of marine autonomous systems comes to be written, it will be the likes of SAISH and L3 and Michael's company, both the Ocean Infinity and the Armada aspects that are the ones that end up being written about. So it's one day you guys will be there in the history books. These were the pioneers that got out there and did it for real for first. So well done, all of you. Thank you, listeners, for listening in and viewing these presentations. We hope that next year we can return to some kind of normality and see you face to face at events and at conferences, and be able to engage with you all in a more face-to-face and normal manner. But in the meantime, stay healthy, stay safe, and please do tune into the other conference sessions that are available on the platform, because there's some really excellent talks out there. So thanks very much.
Yeah, thanks, Steve. Appreciate it.
Thanks.